Alrighty, in this video, we are going to be talking about exponential differentiation in terms of e functions and bases other than e. So thinking back about Unit 2, remember that if we have e to the x, the derivative is just e to the x. Now let's say that you have a function as your exponent. Let's say that you have g of x. Then remember, using chain rule, your derivative of that is going to be e to the g of x times g prime of x. Nothing too hard there. Now your integral, remember that if you have, let's say, e to the g of x, and then you have g prime of x, in this case, and this is going to represent like dy dx right here, then, or let's say du, or use some function, then that's going to be equal to e to the u plus c. So u is some function right here. Your new lesson for the day is going to be bases other than e, and this is going to be a constant base. Now we'll see what happens whenever you don't have a constant base. Let's say that you have a function as a base. If you do, then we're going to have to use logarithmic differentiation that we did back in day 1. But for a constant base, let's say that you have b to the x, where b is some number. Then your derivative here is going to be the same thing, very similar to e, where you have b to the x, but then you have ln of b. If you have a function, however, let's say that you have b to the g of x, then that is going to be b to the g of x ln of b times g prime of x. There you go. All right, so if you do that, then the integral of b to the u ln of b du dx is going to be b to the u plus c, whatever u is, in this case, our function. In addition to that, let's say that you want to find the derivative of b to the x. The integral of b to the x dx is going to be 1 over ln of a times a to the x plus c. So you might need that in terms of what we will have in the next couple of problems. Now, like I said, if you have a function as a base, so let's say that you have cosine of x, and that's raised to sine of x, then you're going to use logarithmic differentiation. So that's y equals. So then you have ln of y is equal to ln of cosine x sine of x, and then you could bring that sign up front, and then take the derivative from there. But we're not going to do that. All right, number 1 is just going to be a little review of logarithmic differentiation. So surprise. Here, remember that we're going to use the properties of logs to expand this. So I have log base 5 times x plus log base 5 of x minus 1 to the 1/2, which will change later, and then minus log base 5 of 2. This 1/2 I could put up front as a coefficient. So now I'm left with log base 5 of x plus 1/2 log base 5 of x minus 1 minus log base 5 of 2. Remember, with log base 5, your derivative here is just going to be 1 of whatever your inside function is. So 1 over x times ln of your base. So 1 over x times ln of 5 plus 1/2, and then 1 over x minus 1 ln of 5. And then log base 5 of 2 is a constant, so you can just keep it like that, aka it's just going to be 0. So your derivative here is this lovely thing. Number 2 should be an easy derivative for you guys to do, because this is essentially the chain rule with exponentials. Shouldn't be too bad. for that one. Same thing with number 3, it's a chain rule, except you want to be careful about taking the derivative of -3 over x. This is not going to be -3 ln of x, because this is not the integral, this is the derivative. So remember, whenever you take the derivative, you're going to multiply the exponents by the coefficient, so that's going to give us 3. That's going to give us e to -3 of x, and then that's going to give us 3 whenever I multiply this, and then I'm going to subtract my exponent, which is going to give me -2. So e to the -3 over x times 3x to the -2. I'm going to skip some of these to find out which one we could take the derivative of. So this one, we could take the derivative of this one. Now, it's important to note, we still need to use our properties of derivatives that we did back in Unit 2. In this case, this is the quotient rule. So the quotient rule isn't going to go away, just like how product isn't going to go away. So this one, remember, low. And then the derivative of high. So this is going to be 3 to the 2x, aka the whole thing, times ln of 3 times whatever my derivative of 2t is. In this case, 2. Also, I just realized that this should be a t, not an x. Oops. So that's going to be the derivative of your top function right here, minus low d high, minus high, which is 3 to the 2t, d low, 1, all over low square. Keep it like this. I am fine if you keep it like this, but if you want to simplify it for the LOLs, which I would encourage you not to at this point, because then you're going to mess up somewhere. I could feel it, and I know that you guys can also feel it too, but this is going to be your simplified version if you choose to simplify. All right, same thing with number 8. If I were to take the derivative of this, I have 3 to the cosine 3x to the 4th times ln of 3, and then I'm going to take the derivative of cosine 3x to the 4th. Now, this is going to be chain within a chain because you have cosine, then you have 3x to the 4th. So we're going to start with the outside function first, which is cosine. So that derivative here is going to be negative sine 3x to the 4th. And then I'm going to take the derivative of the inside function of that, which is just going to be 12x to the 3rd power. So if I were to clean this up a little bit, oops, you would get this lovely derivative right here. Honestly, they're not bad whenever we're taking the derivative. It's just like you gotta remember the chain rule for these. Number 9, we want to find the equation of the tangent line of y is equal to 5 to the x minus 2 at x is equal to 2. What I want you to do is pause this video, try it out, find the derivative of this, because remember, that's how we find slope. So do that, and then play this video once you are done. Your derivative here is going to be 5 to the x minus 2 times ln of 5 times 1, because my derivative of x minus 2 is going to be 1. I want to find the slope of the tangent line at x is equal to 2, so I'm going to plug in 2. So at 2, I'm going to have 2 minus 2, ln of 5 times 1. 2 minus 2 is 0, so I have 5 to the 0, ln of 5 times 1. So that means that this is 1 right here, because anything to the 0 power is 1. 1 times ln of 5 times 1 is ln of 5. So your slope is ln of 5. We have a slope. We need a point. We already have half of our point, which is 2. To get the other point, we're going to plug in 2 here. 5 to the 2 minus 2 is the same thing as 5 to the 0, which is just 1. So I have a coordinate of 2, 1. We have a point. We have a slope. Guess what? Point-slope form. So y minus 1 is equal to ln of 5, and then x minus 2. Number 10, you're going to take the derivative of this. Shouldn't be too bad once again. So the derivative here is going to be 2 to the negative x, ln of 2. And then if you take the derivative of negative x, that's going to be negative 1. So I'm going to plot that right here. #16, same process. So go and pause this video and then play it once you get the derivative. That is going to be your derivative here. All right. So that's the end of the video in terms of exponential differentiation. And once again, not that bad if your base is a constant. So make sure that your base is a constant so that you do all of this good stuff. If you can't, well, then we're going to have to use logarithmic differentiation, which is no bueno.